Someday, a manned trip to Mars and return may become the mission assignment. Exactly how it would be carried out depends upon a number of factors. But here is one way it might be done with nuclear rocket propulsion, using the technology developed for earlier missions. For the first time, men from Earth will set foot on another planet.
At the height of the space race, anything felt possible. It seemed inevitable that the imminent moon landing would lead on to crewed missions to Mars and routinely sending spacecraft to the far reaches of our solar system. A key technology for enabling this would be nuclear-powered rockets, which would offer several advantages over the chemical-powered rockets of the Apollo era. It's a 20th century story that has recently taken a new twist.
It was at the AEC's Los Alamos Scientific Laboratory, high in the mountains of New Mexico, that the first steps were taken. Here, in the mid-1950s, scientists set about to determine if nuclear energy really could be used to provide rocket propulsion. Theoretical studies and early experimental work revealed many problems that would have to be solved. Problems in reactor design, material, radiation, structures, control, to name but a few. The nuclear rocket was found to be feasible.
This provisional work and experiments to adapt nuclear reactors led NASA and the US Atomic Energy Commission to launch the NERVA program in 1961. Its mission was to design, build and test complete rocket engines based on nuclear fission.
That's one small step for man, one giant leap for mankind.
In hindsight, the space race was pretty much done once Neil Armstrong took those historic first steps on the 20th of July 1969. And by the early 1970s, economic priorities and political focus were being dragged in other directions closer to home. Cutbacks to the US space budget meant that Apollo 17 in 1972 was to be the last time anyone would set foot on the moon. And the NASA nuclear propulsion program was curtailed the same year. But the dream of nuclear-powered spaceflight never fully went away. Today, there's a resurgence of interest. We're living in an age of renewed ambition for spaceflight, driven by the disruptive influence of private companies and other nations wanting to get in on the act. There's a feeling that we can do things differently. In 2020, the US government awarded almost $100 million to 3 firms to work on the Draco program, which in its first phase aims to fly a nuclear rocket above low Earth orbit. Essentially, it's the same tech first developed in the 1960s, nuclear thermal propulsion.
Nuclear power sources are compact, reliable, and provide a tremendous amount of energy to power and propulsion systems for a very long time on space vehicles that are often mass and volume constrained. This is a challenge with chemical systems. They become mass limited when you look at the amount of fuel that would be required for deep space operations. They are also not very fuel efficient, so you're very quickly going to use up the fuel that you have on board.
Rocket engines generate thrust by expelling very hot gas from a nozzle at high velocity. The expulsion of this gas generates thrust, which in turn accelerates the rocket in the opposite direction. Specific impulse is a measure of how efficiently the rocket engine generates thrust. Specific impulse is the length of time in seconds that a given mass of propellant can generate 1 g, 1 gravity, of acceleration in a rocket engine.
If we look at the available propulsion systems today, so the conventional propulsion systems, we have on one side chemical propulsion, which can show significantly high levels of thrust, but relatively low levels of specific impulse. And on the other side, we have electric propulsion, which can show important levels of specific impulse, but very, very low levels of thrust. So nuclear thermal propulsion is one of the technologies which can sit in the middle between these two families of propulsion systems.
An alternative approach is nuclear-electric propulsion. Here, the fission energy would ionize a gas that would be fired out of the back of the spacecraft. Although NEP rockets would have far less thrust than an NTP rocket, the two approaches could be complementary.
The types of missions that can benefit from a nuclear-electric propulsion system, for example, are those missions intended to reach the outer planets such as Uranus or Neptune, even Pluto. These missions may include orbiting the planets and taking measurements, maybe even getting samples and returning them. That is something solar and chemical systems really struggle with if you look at these space operations in extreme environments.
The European Space Agency and the UK Space Agency are also looking at nuclear engines. Surely some healthy competition and international cooperation can only help the dream of nuclear-propelled spaceflight becoming a reality.